All right. So every single question that we did yesterday was you invest the money up front, it grows over some time, and you take it out at the end. Or you borrowed up front, it grew, and you paid it back in the end. But we always started with the present value and found out a future value. Today, we're going to look at the same kind of problem in reverse. Sometimes you might have a savings goal, like I need $10,000 in 4 years to buy a car or maybe have some money for college. What do I need to invest now? That's a legitimate question, but it's different than what we did yesterday. So we're going to start by looking at a problem we already have the tools for solving, and then we'll look at another problem in a similar way. So this first example, you guys know how to do this after yesterday, but again, I'm just trying to reframe it with a visual here. So Asher got $500 from Granny and Grandpa over the course of a few years, and he took it all out of his piggy bank. And if this was my home, his brother Bryden would find some way to steal this $500. But he kept all 500, and he's going to put it in a bank account that pays 6%. We're keeping it simple, compounded annually. How much will he have in 5 years? So really, what's going on here is Asher starts with, when you use my nice pink color, Asher starts with $500. How much does he have after 1 year? So what we would have done yesterday, we would take that 500, and because the interest rate is 6%, and it's annually, so we don't need to do any dividing here, we would multiply by 1.06. And then to get it after 2 years, we would multiply by 1.06 again. But we would just write that as 1.06 squared. And we'll just fill up our timeline. You guys have better fine motor skills than I do. I know what I can do. And look at this. This is a big brain, galaxy brain moment. If I zoom in, I can just write bigger. Yes. 1.06 to the power of 3. I mean, you guys get the idea. This is nothing new. And after 5 years, we would have 500 times 1.06 to the power of 5. And that would give us this is a visual of what Asher's investment would grow to. And then how we would have done that problem, yesterday using a table. Let's just do that now real quick. The principal is $500. The interest rate is 0.06. Now, if you're a creature of habit, this is an annually problem. Some people like to just write the divided by 1. You don't really need to. That still gives you 0.06, but I'm not your dad. You do what you want. And then it's 5 years. Again, some people just like multiplying by how often you calculate interest. 5 times 1 is 5. Obviously, interest is calculated 5 times, just like our timeline. And then you can see using the formula, we get the same calculation that our timeline showed us, 500 times 1.06 to the power of 5. Nothing about what we've done here is new. We're just reframing the problem with a little visual. Whatever this is, 500 times 1.06 to the power of 5. $669.11. You guys get that too? Nod and smile. All right, so I'll just make a little conclusion here. Asher would have $669.11. Not bad for an 8-year-old. Okay. So again, we should all be quite comfortable doing questions like these. We've visualized with the timeline, but here's where I'm going to pose a new kind of problem to you guys. So here we go. Let's say instead, Bryden, so he doesn't have a certain amount of money that he's going to invest and have saved up. He wants to have $5,000 saved up in 5 years. How much would he have to invest now to have that much? So it's a bit of a different problem. The timeline looks a bit different. So this question, we actually know what he wants to have in 5,000 years. 5,000 years. In 5 years, he wants $5,000. We don't know what he has to invest, but we have a variable for that. I'm going to pop in a P. After 1 year, whatever Bryden's investment would be that investment times 1.06. And then in 2 years, 1.06 squared. And in 3 years, 1.06 cubed. And in 4 years, 1.06 to the power of 4. And then finally, what we get is, after 5 years, I might just rejig this. After 5 years, we have that principal times 1.06 to the power of 5 has to be equal to $5,000. So it's still the same structure, kind of the same formula that we've been using, except this time we're given the A and we have to find the P. So I'm going to show you guys how we can derive a formula that gives us that. And you know what, actually, you guys know how to, like, if we were trying to get P by itself here, we're multiplying by 1.06 to the power of 5. You guys know how to isolate P. If you're multiplying and you want to get it by itself, then you would divide. Can you guys actually just finish this off? Do 5,000 divided by 1.06 to the power of 5. This would tell you how much Bryden would need to invest in order to have that $5,000 divided. I multiplied by 5,000 divided by 1.06 to the power of 5. So I got, squeeze this in, $3,736.29. Do you guys get that too? All right. Now, we don't want to have to use a timeline for all these problems. So I'm going to show you guys how we can massage the compound interest formula to find present value. And there's a certain way we do it in both of these courses to maintain the kind of same structure as yesterday. I have a lot of space for this. I'm going to go 2 stages here. So if we take our compound interest formula and we want to get P by itself, all we have to do is divide both sides by 1 plus I to the power n. Just do it to both sides. This actually, and then the 1 plus I to the power of n on the right-hand side would divide out. This leads to a formula for finding present value. It's just, instead of multiplying by 1 plus I to the power of n, you divide by 1 plus I to the power of n. But in our course, both of our courses, the 3M, 3U, in the Ontario curriculum and most other resources you'll look at, that's actually not the formula we use for present value. We're going to write that a different way. Because you guys remember from last unit, when you have negative exponents, it's like flipping the base. We're going to actually we're going to go in reverse here. If you flip 1 over 1 plus I, you get the following. You can write this as P equals A, not divided by, but you can write it as times 1 plus I. But instead of having 1 plus I to the power of n on the bottom, you can have 1 plus I to the power of negative n as multiplication. Those last two are equivalent because of our negative exponent rule. And since I have the space, I might just add in, recall, a to the power of negative b, this is from last unit before the break, is like 1 divided by a to the power of b. We'll just use that in reverse. Why do we do that when a divided by 1 plus I to the power of n would work just fine? Honestly, it's just to maintain a similar structure to what you've already been doing. So that's it. That's the new thing. We can now do new types of problems where we want to find a present value. So let's verify that using the negative exponent gives us the same answer. So can you guys pop in your 5,000 for your future value? Our I, it's the same values as the Asher question. I'm going to continue to write divided by 1 just to be consistent. And then it's 5 years, but annually, so I will multiply by 1. Yeah, it's much the same calculator work as yesterday with a new little feature. When you're finding a present value, you're going to use a negative exponent. So can you guys give that a try? Do 1.5000 times 1.06 to the power of -5. You should get the same value we got using the timeline from up above. It should give you the same answer. Yeah, I got the same answer. 3,736.29. And just to be consistent, I'll write a conclusion, really brief one. But this is neat. He would have to invest 3,736.29 to have 5,000 in 5 years. I would say a useful type of problem. Again, later on, because this isn't quite realistic, like I don't know many people who would have several $1,000s to just invest up front. What would happen in reality is you might invest a little bit every week or every 2 weeks or every month, but we have to start somewhere. But yeah, new type of problem you guys should be able to do. So what we want to do today, we want to get comfortable using this new formula to solve this new kind of problem, and also we want to get comfortable looking at a question and figuring out, am I asked to find a future value or a present value here? So can you guys give this new formula a spin for this one? So we want to have $10,000 saved up in the future. I'm giving you a lot of prompting here. I'm telling you, hey, in this question, they give you the future value, $10,000. I'll use a comma. Interest, 4.8, which is like 0.048. Monthly, we divide by 12. And it's 4 years. 4 times 12. You guys give this new formula a spin. Remember, we want a value here that's less than 10,000. All right, so that's 0.004, 48. So 10,000, 1.004 to the power of -48. Same keystrokes as yesterday. That's good. It's just a negative exponent. So just let me, if you forget and use the positive exponent, so if you got 12,112.07, you just forgot the negative. And this would be weird. Like if I was a grade 9 student and I put in $12,000 and in grade 12 I only had $10,000, that would suck, right? So obviously using some critical thinking here, something went wrong. If that happens to you and you're finding a present value, just make sure you use the negative exponent. So what we should get is something less than 10,000 to the power of -48. So I got 8,256. This is sounding more reasonable. $8,256.23. Did you guys get that as well? It's very similar to yesterday. It's just we're finding a present value. We're using a negative exponent, and we showed why we use a negative exponent in this rearranged formula. Okay? So, conclusion. They would need to invest $8,256.23. We'll leave it like that. Again, I know nobody has that up front. I'll show you guys in just a few days how we can do problems where we start with nothing and we invest a bit over time. We have to start somewhere. However, this kind of calculation does have applications all over the place. So I know, well, might not be true. Some of you guys may have gone out and bought some furniture or something for your bedroom or what have you. But when you're an adult, and you go buy furniture, you can buy furniture and borrow. You don't have to pay for the furniture up front. They'll let you pay back something in the future with some interest added on. But sometimes, if you pay cash, they will actually let you pay a little bit of a discount based on, because what the idea is, if you pay a business cash, well, then they have that money to invest themselves, and that money will grow over time. And in the 2 years or what have you that you would have paid them back, you get the same amount. So instead, they give you a little bit of a cash discount. So we're going to do that here. So Lisa owes $1,400 for some office furniture. So $1,400. The amount is due 15 months from now. So the business is going to accept payment now. So like cash right now, so that the business has cash. Businesses like having cash on hand. They don't like it when people owe them money because sometimes people don't pay that money. Discounted at an interest rate of 6% per year, compounded monthly. So it's the same thing we've been doing. It's 6%. It's compounded monthly. We divide by 12. I'm giving you guys nice round numbers still. So that's 0.005. And instead of paying, and it would be due 15 months from now. So you guys can imagine 15 months of interest calculated monthly. This would just be n equals 15. It's just given in the problem. Sometimes those ones can be the toughest, where it's not the years. They just actually give you how many compounding periods there would be. So we're going to use our formula to find out what Lisa could pay right now, a bit of a discounted price if she's paying up front. 1.005. We are using negative n, so negative 15. It'll be less, and that's okay. 1,299.08. You guys get that too? No complaints, but blank stares. Let me double check that. Times 1.005 power of negative 15. Yeah. So let's do our concluding statement and then just kind of make sure we have that digested. So Lisa could pay $1,299.08 right now. Okay. So let's talk about why this makes sense. So let's say you own a small business, and let's say you do a job for that person. So it's selling furniture, you perform a service, what have you. This person, your customer owes you $1,400, and you say, hey, you can pay me $1,400, it's due in 15 months. Instead, if your client gave you $1,300 right now, you might say, well, that's bad. I'm getting $100 less money. But it's not that bad, actually. One, you have the cash, so you know you're paid. And secondly, you can just invest that $1,300 wherever you want to have the $1,400 you'd have anyway in 15 months. So the business really doesn't lose money or gain too much money, but they get the peace of mind of having that client pay. So this kind of process is used all the time. All right, can you guys give this last question a spin? An interesting question. If you wanted to have $1 million in 50 years, so I think you guys are 15, 16, so being retired by 65, 66, not unreasonable. So maybe some of you guys have the cash right now that you could just invest and have $1 million, although $1 million will probably buy you a loaf of bread in 50 years. But anyway, it's an interesting question nonetheless. You guys try this one, and I will pass around some practice. I'll pause recording. You people watching at home, you should give this a try. How much do you need? Is it reasonable? $1 million. Do you guys know who Dr. Evil is? Dr. Evil, $1 million. Austin Powers, no? Do you guys know, are you familiar that there are movies about Austin Powers? Yes? Yeah. Anyway, I digress. 5.2% compounded bi-weekly. Don't think we did a bi-weekly problem today, so that's 26 times a year. 0.002. 50 years bi-weekly, that is 1,300, question mark. It's late in the day. It is 1,300. All right, so what would you need to save up? $1 million. 2 commas. 1.002, and we're finding a present value, so negative exponent. Drum roll, please. Maybe we can pool our money. If you haven't spent it all on Bloxburg yet. Negative 1,300. You know what? That's less than I thought. Did you guys get 74,466.68? Okay, so I mean it is a lot, but you know if you $75,000 you put in right now in 50 years at that rate, that would grow to $1 million, growing by a factor of about 12 or 13. So not too bad. But yeah, so if you were wondering how much you need to invest right now to have to be a millionaire by the time you're 50 and do nothing, it's that much. So we'll just wrap things up. You have that much? I wish I had that much. You would need to invest 74,466.68 right now. So not very feasible. However, in a couple of days, if you guys can wait that long, we'll actually see how it can be manageable if you invest a little tiny chunk of money at regular intervals over time. But we got to start somewhere. We're starting with the present value formula. All right. People watching at home, see you soon. And then you guys in class, you're just practicing, making sure we're solid with the present value formula.